All right. Testing. Testing. Okay. It's working, I think. All right. DC circuit analysis. We're going to go over section 4.5 series voltages and 4.6 voltage dividers today. And today the two labs are due by 3. And we're going to finish going over the homework. Let's go over the homework. So if you have your lab, go ahead and turn it in when I call your name. And also show me your homework if you did your homework when I call your name. Corey?
His labs all been done.
Okay, 10 and 11. I don't need this one.
You don't want this?
No, just 10 and 11. Okay, thanks.
And then this was 36. I realized I did the wrong one. 33, 35, 79, 41, 43, 45.
Okay. Any problems with that one?
It's kind of the last one.
The last one?
I had, after working again with him over there, I saw what I did wrong, but
Okay.
you know,
All right.
get this step.
Dakota?
Here's lab
Thanks.
and my homework, 4.3357. Now I skipped 441, I had to go back and do it.
Okay. All right. Jesse? Christopher?
Lab.
Okay,
I haven't
thanks.
done my 33 through 45 yet.
Okay. All right. Frederick? Did he leave? Oh, he said he had to go, didn't he? Robert? Did he? You don't have your lab?
No, I'm not lab.
Okay. Gary?
I had to look to see which ones it was.
Oh, that's your homework? Okay.
I got that. 3. I only got 4 of them done.
Okay. Thanks. Do you have your lab? You're going to turn in by 3?
Talking about the
The ones that we worked on the other day?
11. Experiment 10 and 11.
Gary? No homework? And Don? There it is. Homework. Okay, thanks. And Clarence? Okay. And homework. Okay. All right. Thanks. So we're going to continue to go over the homework that we didn't finish. We have 2 more problems left, 4.29 and 431. I'm going to try to write bigger today because it's hard for the camera to pick it up. But so the problem says find I and VAB. So we have a 1K resistor, we have a 12 volt source or battery, we have a 4K resistor, another battery, then we have another resistor, 3K, and another battery, 6 volts. Then on the top we have another resistor, which is at 2 kilo ohm. We have a current I reference direction that has been given already to us. And we have yet another battery that's 8 volts. And the reference direction for all the batteries are given, of course. The first thing we're going to do, we know we're going to do KVL because we're in the section on KVL. So that's the rule that we're going to use. Kirchhoff's voltage law. Okay. And we're going to start this problem the same that we did the other one. We're going to start probably at the bottom left-hand corner and go around. But you can start anywhere, like we said before. But before we do that, we need to assign a reference polarity across the resistors, and we're going to use the passive sign convention. So that means that as we go around in the direction of the current, we're just going to do plus minus, plus minus, plus minus, because that's going to indicate that there's a voltage drop across the resistors, which is the passive sign convention. So as we go around, I'm going to put plus minus, plus minus, plus minus, and plus minus. And that's going to indicate the voltage across. So whatever we calculate for the voltage there, that's going to give us the polarity of that. So if I start in the bottom left-hand corner, we also need to indicate, in this problem, they indicated that this was called, they labeled this node B and they labeled this node A. So that's the only other thing. So start here, we get, what do we get for the first thing? Going this direction? Minus 12 volts. Since these are all going to be voltages, I'm just going to leave off the units. Everything's going to be in volts. So I'll just say minus 12. What about here?
I times 1 bigger than K.
Yeah, the I, so the voltage across this resistor is I times R. So I'm going to put I times R. I don't know what I is, so I have to leave it as a variable. And is it going to be a plus or a minus? It's going to be a plus. Okay. So plus I times 1K. And then we go around through here and we get what? Minus 8. And then here we get
Plus I times 2.
yeah, plus I times 2K. You can put parentheses here if you want. Then we continue to go around, we get what? Gary, what do we get right here? Plus 6. How about Robert? What do we get when we get to hit this point? Okay, so what's I? Is it a plus or a minus? Okay, so tell me what to write. Plus what? I times R? But what is R? 3K, okay? Times 3K. We continue to go around. What do we get when we get here? Dakota, when we get to that one? We're going this way. What's that? Minus 4. And then we continue to get through here. Don, what do we get right here?
Plus I times 4K.
Plus I times 4K. And Corey, what do we do after that?
0.
Equals 0? Okay. Equals 0. So that's a pretty long equation. I don't even know if the camera is going to pick up that entire equation, actually. But now what we have to do is we have to group the terms, group all the voltage terms on the right side of the equation, and all the I terms, the terms that have an I in it, on the left side of the equation. So what we can do is we can say I, put parentheses, we can pull out all the I's from here. We can say 1K plus 2K plus 3K plus 4K equals, and then what do we do when we move all the voltages over to this side? You change the sign of it. Yep. So 12 is going to give you plus 12. The 8 is going to give you plus 8. The 6 is going to give you minus 6. And the minus 4 is going to give you plus 4. Yeah. Now that winds up giving us I is equal to, now we take all these terms inside of the parentheses, we move it to the bottom of the equation on the other side, put it in the denominator, is what it's called. And in the numerator, we add up all these terms. So that's 12 plus 8 is 20. Minus 6 is what? 14 plus 4 is 18. So that gives us 18 volts over. Oh, I thought you were leaving. I didn't know you were going to be here.
Yeah.
Okay. Do you have any homework?
I don't think I've got it with me, Mr. Halstead.
Okay.
I'm sure I don't.
And what about your lab? You finished the lab 10 and 11?
I think yes, sir. I'm pretty sure.
You want to turn it in?
Yeah, I'll get it.
Okay. Okay, so then we got 4, 5, 6, 7, 8, 9, 10. So 10K. So what does that give us for? Someone want to tell me what that'll be? Yeah, 18 divided by 10 is 1.8. And the K on the bottom gives you milli. And since we're talking about current, the units is going to be amps. Put a box around it. That's your final answer. So this was part A. Part A was find I. Part B is to find VAB. So we want to find the voltage between A and B. So how can we do that? Yeah, multiplying the I times the R on each one of the resistors, and that gives us a voltage. And then we can just simply sum the the voltages, but we have to make sure that we use the right polarity. So what would be the voltage for this one, the 3K resistor? 1.8 times 3K. Can someone do that for me? We'll figure out what that voltage is.
5.4 volts.
5.4 volts. Okay. And since one thing the eye tells us, right, is that the current is actually in the direction that the reference current is saying. So the actual current is in this direction, right? Because if this was minus, it would tell us that the actual current is going this way. So the actual current is going in this direction, which tells us that the polarity for this voltage is actually correct because we use the passive sign convention, right? Okay. So the actual voltage is 5.4. So that means if we take a voltmeter and we put the red lead here, the black lead here, we're going to get a positive reading on the voltmeter, not negative. But if we put the positive lead down here and the black lead here, the voltmeter is going to tell us a negative reading. Yeah.
So we just add the resistors together and multiply by the current. And we should have the voltage on that side.
Well, we can use Kirchhoff's voltage law, but we still need to know what this voltage is. So what is this voltage? 3.6 volts. Okay, so let's write a KVO equation around this. Now you can either do this loop or you can do this loop, but either way it should be the same because your loop is going to be VAB is in the middle, right? You're basically wanting to measure across here with your voltmeter. So you can go around this way and add up those, or you can go around this way and add up those. Either way should give you the same answer. Okay? So I'm going to do this one, and then if you want, we can do this one as well, and we can see that it gives you the same answer. So if we go this way, if we go through this minus VAB, then we get what? Minus VAB. Okay, this is a minus. That's the voltage we want. And then we get a minus 8. And then we get a plus 3.6. And then we get a plus 6. And then we get a plus 5.4. And then we set that equal to 0. So what that tells us basically, once we move the minus VAB to the other side, then everything is going to be just equal to that. So we get VAB is equal to minus 8 plus 3.6 plus 6 plus 5.4. It'll be minus 8 plus 3.6 plus 6 plus 5.4, which would give us what? This gives you what, 9?
Gives you 7 volts.
Yeah. Gives you 7 volts total if you add it up. Now, do you guys want to go this way? Let's do this way and add that one up, just to see if it gives us the same thing.
You gotta make it take those.
This one was 6. Okay, so let's do this loop. So we'll go through here. We'll say minus VAB, right? Okay, then what? We have to know what this voltage is. This voltage is going to be what? 1.8? This voltage will be what? 4 times that? Can someone give me that one? What's the voltage across the 4K? 7.7? Huh? 7.2? 7.2. Okay, so as we go through here, we've already done the minus VAB, we get minus 1.8. plus 12, right? Minus 7.2. And what? Plus 4 equals 0. Now when we move this to the other side, then we get VAB equals minus 1.8 plus 12. Is that right? Plus 12. Minus 7.2 plus 4. And if we add all those up, what do we get? Did you guys actually add it? Let's make sure it actually does. We're going to do 12 plus, or minus 7.2 plus 4 minus 1.8. 7. So it's exactly the same, right? So we just proved that it doesn't really matter which way you go, Kirchhoff's voltage law will work.
What makes the VAB minus?
Because you're going through this minus sign.
Yeah, well, yeah, you assigned that, but how do I know that that's a minus sign?
Because it says find VAB. If it said find VBA, VBA would be like this.
Plus would go on the first letter.
Yeah. Yeah. Yeah, it's in the order of A is considered your most positive and B is considered your most negative. So really the definition of VAB is actually VA minus VB. That's the definition of VAB. And of course this, when you say VA minus VB, that would be reference to some arbitrary ground, which it doesn't really matter what that ground would be. We haven't really talked about ground yet. We want to talk about it today. Or actually not today, but we'll talk about it the next session. We'll talk about reference grounds, and that's what we mean when we say VA or VB. It's always reference to some sort of a ground level. Yeah. Okay. Any questions on that one?
Basically, you just cut the circuit in half at the place where they put the loads and then short circuit it. Figure it that way.
Well, you don't really short circuit it. You leave it open circuit. But you're calling this VAB. You're assuming that you're putting a voltmeter across it. A voltmeter is like actually very high impedance. Has a very high impedance, not low impedance.
But your mathematical calculations are done as if those two were connected together.
They are. That's two separate ways.
Well, just consider this as a voltage source, I guess you could say.
Okay.
Consider that a voltage source. Yeah. .431. Actually, 431, when I worked this one, there's some problems with this problem, but I wanted to go over it just to let you guys know. There's some issues with this problem in the book. And so the answer in the back of the book is wrong on this one. And there's more problems. There's issues with this problem, so I'll go over it with you guys. Find I, and then the B part is find XY, and then the C part is X or Y higher? Question. Oh, I'm sorry, find VXY. Find VXY. So what we have is a 3 ohm resistor 2 ohm resistor, a 20 volt battery, (11 ohm resistor, reference current as indicated down, a 4 ohm resistor, and a 5 volt battery. And we're going to call this node Y. We're going to call this node X. And so the part A is find I. And we're going to use Kirchhoff's voltage law to do that. So KVL. Actually, what I'd like to do here is an activity, let you guys work on it and see what you get. Strictly using KVL, the same thing we just did, do your loop around here. What I want to see is the equation, the first equation. That's my main concern. Write it in big letters so I can see it. And once you get that first equation here, raise your hand so I can come look at it, and then you can go ahead and solve it after you get the first equation. You got it? Oh, well, it's quick.
This is where I was ran into the problem last time. So I'm going from the bottom, so plus 432, and then negative 20.
Oh, wait, I'm sorry. I put the polarity on there wrong. I put it right, but the book has it wrong. That's the right polarity, but the book actually has it like this. And which is backwards, which, first off, that's wrong. It's totally wrong, but that's the way the book has it, so we're going to leave it like that. We're going to leave it wrong.
So is this wrong then? Or is this right?
Okay, so you got plus 5. Oh, so you're going from there. Okay, plus 5, and then you get, what is that? I times 4?
Mm-hmm.
What polarity did you use? Did you sign a passive sign convention? What's the first thing you guys do when you look at this problem? What do you have to do? You have to put your reference polarities on here, otherwise you can't even work the problem. That means you go around the direction of the current, you go plus, minus, plus, minus, plus, minus. Not minus, plus, plus, minus, right? If you go minus, plus, it's wrong. For this reference current. We don't actually know what direction the current is, but if we say this is our reference current, then we need to assign the passive sign convention based on that current, assuming that the voltage is going to be dropped. Now, if it turns out the current's flowing this way, then we know this current is wrong and all of our voltage references are wrong, but we have to have a starting point from which to work. So we do plus, minus, plus, minus, plus, minus. And then, of course, plus, minus. So write your first loop based on that.
That's how it is. Equation.
Okay, so I4, I3,
2.
minus 20.
I love it.
What is that?
Plus.
C?
No, there's parentheses.
Oh, okay.
Yeah.
Oh, okay, equals 0. Okay, that's right. And the answer you got, that's right. Anyone else? You got it. Minus. Where do you start when you
I
did?
started at the voltage sources.
Oh, okay, you started that one. 20, 11, 5, 4, I3, I2 equals 0. Yeah, that's right. Now you can group them, right? What is that? Okay, so then, yeah. So I is going to be equal to what? 15. Yep, that's right. What did you get? This is your loop? This is your loop? What did you do? You started at the 5? Okay. What did you go this way? Oh, you went that way. Okay, so, but your reference polarity on your resistors is wrong, but, right? Because the reference current is going this way. I is going this way. Yeah. I mean, because it says I is going that way. I mean, it doesn't matter. I mean, it'll still work out, but here. So you're saying I is going this, the problem says I is going that way. Okay. So you're going to say, first off, is that an equal sign? That's a problem because you can't have two equal signs. Yeah. Yeah, it has to be, yeah. Yeah. So if you're going this way, it would be 5 minus I4. Where's that at? Or you can go this way. I think you went this way.
Yeah, I went that way.
So it would be minus 5. So it would be minus 5 plus I11 plus 20. Yeah. Yeah. Yeah, just redo that one. Let's see what you got. I think you're missing a resistor right there. Anyone else done with it? Okay. I3. I3, I2. Is that a minus?
Minus 20.
Okay, minus 20 plus I11 plus 5 plus I4 equals 0. That's right. And actually, the only thing wrong is it's supposed to be a 20, not a 19.
Plus 4 is 15. Oh, whoops. Okay.
Okay. That's good, though. You got it?
I started at X.
Okay, you started at X. So you got
Using their
minus
polarity.
20.
Minus 11 times.
Minus.
Times 11.
Can you put a plus over here on that side?
Oh, okay. Well, I figure if it's minus over there, it's going to be plus.
Minus 11 plus 5 minus 4. Is that a minus minus?
I don't know. I just put a minus, and then I said, oh, wait a minute, I forgot my parentheses, and I put parentheses.
Oh, okay.
Wait,
So
do it again.
minus I3 minus I2 equals 0. Okay. You can go ahead and solve that one.
I got it solved on this.
Some people didn't use the passive sign convention, but it's okay. I mean, if you don't want to use the passive sign convention, it just makes the problem easier. That's right. What'd you get for the I3 plus 2 minus 20, 11 plus 5, 4 equals 0. Okay, that's right. So, I'm going to go ahead and give you the solution to this one. So what I do is I start here. I usually start at the bottom left corner. I don't know why. Some people start wherever they want. But what I got was 3i going through here plus 2i minus 20 plus 11i plus 5 plus 4i equals 0. Okay, then we collect the terms together. We move all the voltages on the other side. The voltages, so we're going to get I, 3 plus 2 plus 11 plus 4. So we group all the I terms together, and then we set that equal to, and then we move all the voltages on the other side, but we reverse the signs. So it's 20 minus 5, right? So now we get I equals to, we take all of the parentheses terms and we move it to the denominator and put it on the other side of the equation. So that gives us 15 over 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. 15 over 20 is 0.75 amps. And the interesting thing about this is that that's a positive number, right? Which means that the current is actually flowing in the reference direction given. Which means if you use the passive sign convention, the polarities for your voltages on the resistors will be actually correct if you measure it with the voltmeter. And if you use something other than the passive sign convention, then you know that those you're going to have to use. There's the other equation of Ohm's law. Remember we had Ohm's law? We had Ohm's law is equal to V is equal to IR if you use the passive sign convention. If you don't use the passive sign convention, V is equal to minus IR. Okay, don't forget that. That's one of the very first things we talked about. Has everyone got that? What that means is for a resistor, remember Ohm's law is all about resistors. If you have a reference I and a reference voltage, if you assign the reference current and voltage in this direction so that the current is in the direction of a voltage drop, then the equation is V equals to IR. If you don't do that, if you have your resistor and you say, well, I is this way, but I'm going to put my voltage in the direction of a voltage rise, then you have to say V is equal to minus IR when you do your equation. Okay? Passive sign convention, non-passive sign convention. Do you want to use V equals minus IR when you do your equations? I don't. So what that means is since we use the passive sign convention, we calculated the current is going in the reference direction. All we have to do is calculate the magnitude of these and put the numbers there and the polarities will be correct. We can use regular Ohm's law without the minus. Now B says find XY. 1140. Let's do the same thing we did before, right? We want to know the voltage. What is it? Don had a good question. How do you know what direction if I say this is XY, how do I know what side's plus and what side's minus? Well, the first subscript on the bottom, the first one to the left, X, that says that that's positive, and Y is the negative one. So you say the X is positive, the Y is minus. So when you do your loop, it depends on which direction you go. You can go whatever direction you want. You can go this way around the loop. You can go this way around the loop. You can do this loop, or you can do that loop. Doesn't really matter. You guys do it right now. Do any loop you want, and let's see if we all get the same answer. Corey, looks like you're done. He's got his hands crossed over here. Okay. Let's see, X, Y. Yeah, that's right. And that's right too. So you got the right answer even though the book was wrong, right?
Yep. That's what threw me out last time. I've been waiting for us to cover this to see what the heck I did wrong.
It seems like the pattern I'm seeing is that the last problem of each set is wrong. Or the last one, like some of the ones on the end, right?
Amperage times the resistance, which is the only one on that leg, equals 8.25.
Only thing is the polarity is not right.
Oh, I have the negative. I forgot to add the negative.
Where's the negatives? Where do you see the negatives?
It's the negative 20.
Oh, negative 20. Let's
This
see.
is minus 20. I don't ignore this.
Okay,
That's
good.
for amperage.
Good.
Minus.
What'd you get? That's right. Which loop did you do?
I did a short one, the one with the 20 volts and
Okay.
11 ohms.
Okay.
Is that correct? Is X the...
No.
Higher in potential?
The right answer.
No, because see, since that number is negative, right?
Mm-hmm.
Since that, if Vx turned out to be positive, then if this number turned out to be positive, then this is indicating, the plus and the minus indicate, the plus indicates that this is higher than minus, if the number is positive. If this number turns out to be negative, then that gets flipped. You see what I'm saying? For positive numbers, for example, let's say I have, this is 5 volts here, and I say this is positive relative to this. What that means, by writing the positive, I'm saying this is higher than this. That's what the positive and negative means. It means that this is higher in potential than that, by definition.
I was thinking in terms of current flow.
But if I were to make this minus, what I'm really saying is this is actually higher than that. Because you have to, it's a negative negative. A negative negative is a positive. It's kind of confusing, but negative negative.
Well, you said that we're treating VXY as a voltage source.
Yeah.
Current, the current flow direction, current should flow out of the positive of the voltage source, so I thought that would indicate that X would be positive.
Well, the current is flowing this direction, right?
Right.
So it would, this would have to be the most positive, because current would flow, yeah, into that. So
That's going to be confusing.
don't think of it like that. Think of it just like the way I said it. This number turns out to be minus, right? So the only way that this X terminal would be higher in potential would be if this number was a positive number.
We assigned it that way because they put X first.
Well, no, we solved for it. You solved for it. You solved for this number using KVL.
Right.
Um,
How did we assign the polarity there?
the person says find X, Y, VXY.
It says find the voltage between points X and Y. Give us a VXY.
Well, if it says that, then it doesn't really matter what you solve for.
So the answer would be XY, VXY is negative 11.75.
You could solve for VXY or VYX. It doesn't really matter. But in the end, you're still going to want to know what side's higher. So is Y higher or X higher? Yeah, voltage between X and Y. So like Corey, what he did was he actually solved for both. Doesn't matter. They're just going to be the opposites of each other.
Right. So once again, how do you determine what the polarity is?
You use KVL.
You lick your fingers and, yeah, you use
Well, that becomes
Really, the ultimate thing that we did here is determine which node is actually higher. All this reference and everything doesn't really matter. Ultimately, what we did was we found that Y actually is going to be higher in potential than X. You can assign whatever polarities you want here. You can go around whatever.
I'm not seeing how we did that. Based upon what? Current flow? Based upon, how did we determine that?
You got the right answer. You got the right answer, right? You got the right answer, but you had to change it. I think for you, it's going to come in the labs. You're going to have to just do it and see it when you do the lab. Like, build this circuit and measure it. I don't think you're going to be able to see it on the board because I know you're always asking those type of questions. Just build the circuit and measure it because that's when it's going to...
With a negative number based upon the way we assign the current flow, right?
If you start from X, you have a negative 20.
Yeah, what we determined is that the current is actually going to flow this way because this number is positive. If it would have been negative, it would have flowed the other way. Ultimately, what we're doing is we're saying the current's flowing this way.
And that's what's determining our polarity in actuality.
Yeah. And next it says find the voltage between these points. And again, you can search for VXY or you can find VYX. But still, regardless of what you do, you're still going to know what terminal is higher. It doesn't really matter what you do. The ultimate goal is to figure out what side is actually higher in potential and what's the magnitude of that. This could be a motor across here. And depending on where you connect the motor, it's either going to spin forward or backwards. So it matters.
I know it matters. I'm not saying that. I'm saying that.
So in this case,
Determine that.
you use Kirchhoff's voltage law
Yeah.
to determine it.
Right, okay. So we came up and we said we had a negative voltage. How do I know which way my meter's connected?
Well,
Based upon VX and V.
what I'm saying is VXY, your meter, your red terminal is going to be here. This is going to be red. This will be black.
But you said that was based upon whether we find VXY or VYX.
Mm-hmm.
Right?
Think about it like this. If you take your meter and you flip it, it's going to give you a minus number. Okay. Okay. This is just keeping track of what you're doing.
I know. I'm not, that's not. I can't look at that diagram and determine that Y is the higher potential than X or X is higher. I'm asking how do I do that?
Yeah. I don't think I'm going to be able to answer your question. We're going to have to move on. I think what you're going to have to do is do more labs, and when you do the labs, you'll start to get a better feel for why it's working the way it is. But let's just make sure that we.
1,000 times in the field, so the lab isn't going to fix it.
Okay. So what we did here to solve this problem is, we use Kirchhoff's voltage law. I'm saying, the question says find the voltage between X and Y. I'm saying, okay, let's find VXY. We can find either one, doesn't really matter. Find VXY. So if I say VXY, then that means, by definition, this is plus, this is minus. For a reference, okay? If I use KVL, I'm going to go through here, or I can go this way, I can go this way or that way. Doesn't really matter. For me, I'm just going to go right through here and go around this loop. I'm going to try to determine what the magnitude of the voltage is. And also tell me the polarity. So if I go minus VXY, okay. If I would have chose VYX, this would have been a plus, but I chose VXY. Go through here, I get minus 20 plus I11, 11I. In this case, what is I? 0.75, which is 8.25, right? So it's 8.25, and that's it. Equals 0, right? So then we wind up with, if we move this to the other side of the equation, right? VXY equals what? Minus 11.75. Now remember that the purpose of doing the circuit analysis is for us to be on paper, to be able to draw something, and to know that we can go back in the back of the room and we can wire it up and we can get the same answer. So what this is telling us is that if we take a voltmeter and connect it red here on X, black on Y, then the meter is actually going to give us a minus, not plus number. That's what it's telling us.
I think the light bulb.
Okay?
Because we solved for VXY and it came out negative, that's what we're talking about.
Yeah.
Solved for VYX, it comes out positive.
Yeah, what this is telling us is we put a red terminal here, black terminal here. Your fluke meter is going to say minus 11.75. And if you reverse those, it's going to say plus. And there's value in that. So we're done, I think. Oh, no, we have one more. So the question is, what terminal is higher in voltage? What node actually is higher voltage? Yeah. Because this is a negative number, with the reference that we've given, we assign this arbitrarily to be higher in potential with a plus and this a minus. But since we have a negative number, we know that assumption is wrong. It actually happens to be the opposite. This is not higher. This actually is higher. If this was a positive number, then we would know this actually is correct and it is higher. That's how it works. So no matter what reference you use, this node is always going to be higher than this node. You could use a ground reference. You could use a ground reference of negative 1,000 volts. It's still going to be true. Good? Okay, we can start the next section. And the next section is pretty easy. Just voltages. And you guys already did the homework, I think, most of you. And I think you guys probably already know this, but it doesn't hurt to just reinforce it. Section 4.5 is a very small section and very simple. It says voltages in series. And the example in the book is you have a voltage source here. You have one here. And then you have one maybe in the opposite direction. We can label this terminal A, this one B. We can call this V1, V2, and V3. And really, we've already done these type of problems. If I define this as, if I want to know the voltage between A to B, and if I say, well, I'm going to assume that A is the higher terminal, which means I'm going to assign this plus and this minus. I can call this VAB. Then I can use Kirchhoff's voltage law to come up with an equation. If I do that, what I wind up with is minus VAB equals what? Plus V1 plus V2 minus V3 equals 0. I'm sorry. Minus V plus. So minus VAB plus V1 plus V2 minus V3 equals 0. If I move the minus VAB to the other side, then I wind up with VAB equals V1 plus V2 minus V3. What it tells us is that when we have voltage sources in series, if you stack them in the proper direction, that is, if you connect the minus terminal of one to the positive terminal of another one, then you will get those voltage sources to add. However, if you reverse the cell, obviously, then that voltage is going to subtract. So in this case, we have a minus terminal connected to a minus terminal. In that case, the voltages are going to subtract from each other, which is indicated by the minus V3. So the total voltage VAB is going to be V1 plus V2 plus V3. Pretty simple. But another thing that I think this stresses is this whole idea of having a reference and the notation of VAB itself. VAB means that you're assuming the A terminal is higher than the B. And so you would assign the A terminal with a plus. And by definition, VAB, again, I've already talked about this, but want to stress it in this section. VAB by definition is VA minus VB. If you're talking about some sort of a reference ground position. So if we say that VA is the voltage between A and some reference point, VB is a voltage between B and some reference voltage, then we can say VAB, or the difference between those two terminals, is VA minus VB. And the next section is voltage dividers. And voltage dividers is really important, and it really helps simplify a lot of the work that we would do. Section 4.6. And basically what it says is, if you look at figure 420, you have a battery. We'll just call it, I'm going to call it VX because I don't like to call it just V. And we have, let's say that we have perhaps 4 resistors in series, and we call those R1, R2, R3, and R4. If we define some voltages across the resistors as, if I define V1 as the voltage across R1, and if I define V2 as the voltage across R2, V3 the voltage across R3, and V4 the voltage across R4, then I can say that the current flowing out of the battery and into the resistors is going to be equal to, according to Ohm's law, I is equal to the voltage X divided by the equivalent resistance, or the total resistance, which would be R1, R2, R3, and R4. So now if I say, what is V1, what is the voltage across R1, it would be what? V is equal to I times R. I times R what? In this case is 1. And I is what we just defined above. So if we substitute I for the equation we came up with, what do we get? We get Vx R1 over R1 plus R2 plus R3 plus R4. In other words, we get that the V1 voltage is going to be Vx over R1 plus R equivalent, or R total. So that the voltage across resistor R1 is equal to the resistance divided by the total resistance in the chain multiplied times the source. And that is a general statement that you can apply to V2, V3, and V4. In other words, the voltage across V2 is going to be similarly, is going to be not R1, but what? R2 over the total resistance multiplied times the source. So it's a very powerful formula, and it can save you a lot of work. Very commonly what we do in many situations is we'll just have 2 resistors. The equation works the same way, but typically we would write that as R equivalent, in this case, would simply be R1 plus R2. This is normally what we consider the voltage divider rule, because it's the most commonly one that we use. In the case of 2 resistors, we would say that the voltage here, V out, in this case, since we're saying it's the voltage across R2, we would say the voltage across R2, in this case, if we call this ground, in many cases we call this ground, then the voltage out of this would be the resistor R2 divided by R1 plus R2 multiplied times the voltage, Vx. And we could call this V out. Okay, so let's work some problems. So let's look at some of the problems. You guys worked
33.
33?
345.
Yeah. So let's start looking at 33. .33 says find the voltage VAB. In the circuit. Now notice in this case they said VAB and they're saying that this is the reference direction. And this is a plus and a minus 4 volts, plus and a minus 6 volts, and a plus and a minus 12 volts. Now this section comes from the voltages in series section, so it's really wanting you to put those voltages all in series and add those up. So if we wanted to find VAB, and if we're saying that this is the reference positive terminal, what would be the total equivalent voltage across this resistor?
It'd be equal to, if you start from the bottom left, you go -6 plus 4, you would be equal to -6. What do you want? You start anywhere, right?
Well, just what I'm trying to do here is say, let's not use KVL. Let's just look at the voltage sources and try to eyeball it and see if we know that these are being added together, and you have to have them in the right polarity in order for them to add. And if they're in the wrong direction, they're going to subtract. So
-6 plus 4.
yeah, so it would be 12 because this one's in the right direction, right? This plus is going to tend to make that plus. So that's 12. This one is in the wrong direction. There's a minus sign, so it's going to tend to subtract from the total voltage of this chain. So it'd be -6. And then here, this is going to tend to what?
Correct.
Add. So plus 4, which gives you 12, minus 2, which gives you 10.
But then you minus the VAB to equal 0.
What's that?
What says -10 for the answer?
It is right.
In the other direction.
It is -10.
No, it's,
I
Minus.
came out with 10 too.
yeah, it's 10. If you put the plus on top, then it would be, but yeah, it's plus. It's plus. So what about the next one? 35. .35 says how many 1.5 volt batteries must be connected in series to produce 12 volts? What do you guys think? Yeah, 12 divided by, you need 12 volts, and what you got is 1.5 volt batteries. Okay? So how many do you need? How do you solve it? Yeah, divide by 1.5. Gives 8. $4.37. Class is over at 11:40. Huh?
I know I can leave right on time though.
Okay, you can go. Go ahead.
You sure?
Yeah.
I can mark it.
Just go ahead, we'll mark you after you leave.
That's one way to.
I'd rather you leave than stand up and start talking to people as you're leaving.
We're actually talking about that.
Okay, but it's disturbing class, though. If you're going to leave, I'd rather you just leave, not stand and start talking to people. You got 2 minutes. It's fine. Yeah, go ahead. No, I'm not going to mark you. Go ahead.
You're already a marked man.
Simplify the circuit of 4.63. Find the current passing through the resistors. So, in this case, if you look at the diagram, all they're wanting you to do is combine all the voltage sources together. And all the resistors together, in this case. So, are the voltage sources tending to add to each other or subtract? Well, I think about the 5-volt source up here. You got a plus 5 here, and then you got a 9, and then you have a minus 2, and then you have this thing going on. Okay, so this one is going to be 5. This one's 2, and this one's 3. So if we get this one 5, this one is going to subtract from it, which is going to give us a total of what? 3. And then if we take this one, what is that going to tend to give us? 0. Yeah. So it gives you 0 volts. So you're going to have 0 current, right? Is that what the book says? Yeah. So let's look at 37 in the back. Let's make sure that 4.37. Yep, 0 volts. Okay. We're out of time. How did you guys do on the voltage dividers? Okay. Okay, so for the next section, what we're going to read is 4.7. 4.7, 4.8, and 4.9. And the problems are going to be let's see, 47, 51, 54, 56, 58, 59, 61, and 63. 1, 2, 3, 4, 5. So we got 8 problems. 47, 51, 54, 56, 58, 59, 61, and 63. And just to let you know, when you read this section, this is kind of the application and simulation section at the end of the book. At the end of each chapter, we're going to have like a computer analysis section and the application section. So this is an opportunity to do a little bit of hands-on computer work and to do like some real-life applications that, you know, it's going to help solidify the concepts. And in this example, they do an LED circuit and a series lamp and a parallel lamp type circuit. So it's very basic, but it applies directly to the concepts we've been learning.
I guess one other thing to get a hold of Dakota and let him know he got homework.
Yeah. Yeah.
You want to do our session? My session is 1 o'clock, or just do it now right quick.
Let's see. Yeah. We could do it now.
That way you wouldn't have to come back. And I wouldn't have to come back or whatever.
Take care, Dr. Austin.
Yeah.
Have a great
Thank you.
weekend.
Appreciate it.
Yes, sir. Appreciate you, buddy.
Yeah. Let me turn off this.
Both
In the
those.
back. Turn off this camera.